So far in section 2.3.1, we've talked about a lot of different strategies to try to evaluate a limit algebraically without the use of a graph. Now, we're going to see here that we have one final idea that we're going to talk about in this section, and that's obtaining limits by quote-unquote squeezing. So here's at least the general idea before we get to what's labeled as the squeeze theorem down below. Suppose that we have the following scenario. Let's suppose that we actually have three different functions. Okay? Suppose we have an f of x, which I'll call the blue function. Suppose we have h of x, which is a red function. And you can tell that f of x is a small function, so it's going to be low down in our picture. H of x is a big function. It's going to be higher up. And then g of x is going to be a function that falls right in the middle. Now, this is going to be true, maybe not for all values of x, but at least all near or around some value of a. Let's try to get a rough picture of what this could possibly look like. So let's say that I have an x and y axis that look like this. And let's say here's the value of a. Okay? And what we're going to see is that, let's suppose that I have a function where f of x that, I don't know, f of x is the small one, so maybe it's going to go down here in my picture. Okay, something like this. Here's my function. It's low. Now my red function is going to be larger. But take a look at what's going to happen here based on this fact, because this is going to influence how I draw my red function h of x. This says that it's got to also be the case that the limit when I approach a on the f of x function, which I can see where the path is leading me, right? It's leading me to kind of right here, this spot. But the limit on the h of x function has to be equal to that. They both have to have the same overall answer. So notice that when I draw my red function and it's much higher in the picture, it eventually has to lead me to exactly the same point, and then it can go off and do whatever the heck it wants. Okay? But now something interesting happens, because g of x is a function that's got to be between them. And if I have these facts set up initially, I think we could make some determination about what's going to happen to the function g of x as I approach the value of a. Notice, if you try to draw g of x in here, you got to stay in between or equal to these functions. So it's okay to be equal, but you can't go past either of them. They're boundaries, they're fences, they're keeping you locked in. And you got to stay in between them. You don't have a lot of wiggle room, and then we have a lot more freedom once we get out the other side. So if these blue and red functions kind of squeeze together at the point of a, what would you guess the limit is for the green g of x function? Well, it looks like it's the same thing. Whatever that value is the same for all three functions. This is the idea of what we call the squeeze theorem. It says if I have, again, my red function h of x, my blue function f of x, and my green function of g of x, and they're in this order, and it's the case that the limits of the outer two things, the small thing and the big thing, are L, then the limit of the middle thing has no choice but to be the same thing. So this right here is a tool. It's something that we can use to help us, but we'll see that it's kind of going to be one of our more last resort tools. We'd really like to try to use other things that we've seen so far in this section to help us, like using direct substitution, or our limit laws, or simplifying our way out of problems, or checking limits from multiple sides. But sometimes it's going to be way too complicated, and the squeeze theorem is a useful tool. Let's take a look at example number 9 to see an instance like this. Let's take a look at this. Oh boy. I want the limit of x squared times the sine of 1 over x, and I want to show that that's going to be 0. Okay. Well, we're going to have some problems here. Okay, first off, this is not a polynomial. I can't just plug in 0. Even if it was a polynomial, I have a problem, because if I try to plug in 0, I'm going to get divide by 0. So I don't even have a fraction though, so I can't really think of a good way to like simplify out of this, or like I have no idea what I would do with this limit. This is the moment the squeeze theorem can be helpful. The hard thing is that we want to imagine that this function here is our g of x. And our goal is to create the f of x and h of x that are going to allow us to figure out what this limit is. Now, here's one way that I believe that I can go ahead and start trying to build these blue and red functions. I don't actually have to guess them. I can almost kind of construct them. Take a look. I'll state that we know from trig that for any x, in this case that's not equal to 0, the sign of 1 over x is always going to be between -1 and +1. Notice that what we have here is like the start of the green thing. That's why I'm doing it in dashed. It's like almost the green thing. And so that means that I'm kind of almost able to imagine a blue thing and a red thing, right? I'm kind of slowly creating this. But I know that this is true because I know trigonometry. But again, I want to create the entire green function on the inside, but how could I do that? Oh, well, here's an idea. What would happen if we multiply everything by x squared? Well, if we did that, let's see how everything would change here. The left side would be -x squared. The middle would be x squared times the sine of 1 over x. And the other side would just be positive x squared, right? That's what it would look like. And what I can see in the middle now is that I actually have my green function fully. It's in there, x squared times sine of 1 over x. And notice that I have wedged it between two outer functions. My h of x is x squared. My f of x is -x squared. And according to the theorem, as long as I can get the green thing squeezed between two other things, and then as long as the limit of the blue and the limit of the red are the same, I know the limit of the green thing. So let's check the limit of both the blue and red function. So I'll say we see that the limit as x approaches 0 of -x squared, well, wait, that's a polynomial. So I can just plug in 0 and I get 0. But I can also see that if I did the limit as x approaches 0 of just regular x squared, that's the red function, that's again a polynomial. I just plug in 0 and I get 0. So notice here, I actually did the limit of the blue function and I did the limit of the red function, and they did come out equal. So here my L is this value 0. So now I know, and I can put this together, I can say, so by the squeeze theorem, I'll write it like this. By the squeeze theorem, the limit of x squared times the sine of 1 over x as x goes to 0 must be 0. Whatever the limit of the other two things were is exactly what the limit of the middle thing is. We got it. That's the squeeze theorem. And if you think about it, that's a really awesome thing to be able to do, because how else were we going to tackle this limit? That's a nightmare. Now what I'm going to ask you to do is to try to take a look here at example number 10 and see if you can try this one out on your own. I'd actually ask you to pause the video right now to see if you can try to work through this, and then when you unpause, you'll see me quickly work through the solution. Okay, well hopefully you did try this one out, and if you got stuck, it's no big deal, but let's just try to take a look at it. So again, we can start by saying that we know from trig that the sine of pi over x, regardless of what x is going to be between -1 and 1, again, as long as x is not the number 0. But notice then, what I have is, again, almost my green function, and then almost my blue, and almost my red. I just need to keep working on this. So let's see. How about I can go ahead and I can make everything here. So I'll say we make each piece here a power of e. So that would be e to the -1, e to the sine of pi over x, and e to the 1. Now, the hard part with doing this is that I have to actually think through if it's the case that the inequalities are still going to face in the same directions. Now, you may or may not have considered this when you did this, but it's a very important step. And it's very helpful to know what the graph of e to the x looks like. This is one of our graphs to know. But y equals e to the x looks like this. And one thing that we can note on it is that whenever you plug in a bigger x, you get a bigger result. So if 1 was the biggest number, e to the 1 should be the biggest result. If -1 was the smallest, it should produce the smallest result. So I can get this. Again, I'm getting a little bit closer to my green function. The last thing I can do is to multiply by square root of x. Square root of x is going to be a positive result, so I don't have to worry about anything in terms of changing directions of signs or inequality symbols. But I end up with this. And so, oops, that should be an x. And so we have created, again, all of our functions that we need. We have our g of x function in the middle. We have our f of x function on the side. And we have our h of x function over at the right. So what we need to do now is to check the limits on each of those. So I'll say, we see that the limit of the square root of x times e to the -1 as x approaches 0. Notice, e to the -1 is a constant, so I can actually just pull that outside of the limit. And so I just have to deal with the square root of x. Remember though, with square roots, you can always just do the limit of the inside. That was that last limit law that we had. So this is really just going to be e to the -1 times 0, which is 0. Notice, I can also do my square root of x times e in exactly the same way. E is a constant, so I can pull it out. And then I'm just going to end up with e times 0, which is 0. And so with both of these together, I can say, so by the squeeze theorem, the limit of the square root of x times e to the sine of pi over x, x goes towards 0, is actually 0. Now it is total coincidence here that both my answers ended up being 0. They may not always be 0 when you use the squeeze theorem, but it just depends on what happens with the limits. Now one final thing that I'll say before we end this section is that you've seen throughout all of the work in this section how much explaining I really have to do. Take a look at just all the solutions that we've had. How many words are in them? Right? I mean, not all of them, but sometimes there are words. In fact, I'd say most of the time there are words where I'm kind of explaining what I'm doing as I'm doing it. And this is what I'm going to expect that you are able to do in this class when I ask you to convince me of an idea. So please make sure that you're aware of that and that you try to practice that as you even work through worksheet problems in the associated sections.